So this is the first video for Unit 8, which is logarithms, and this video will be on the properties of logarithms, which is the first topic in this unit. Before we talk about properties of logarithms, I want to talk about properties of exponents. So just to recap from the last unit, if we have a base b raised to the power x times base b raised to the power of y, we can rewrite that as base b x plus y. And because of this for exponents, we can relate this to the product property for logarithms. So if we look at this from a log standpoint, we have log base b of x times y. We are able to expand this and rewrite it as log base b x plus log base b of y. So in our argument, we have x times y, so we can expand this using addition. And again, that stems back to the properties of exponents here. And the reason why we utilize these properties is because it makes complex arguments for logs simpler to evaluate. We are able to solve this easier having one part in our argument rather than both parts. And then the next one is the quotient. Again, if we think back to exponential, we have base b x divided by base b of y. Because they have the same bases, we can rewrite this as as b raised to the x minus y. So for our quotient property, we will use subtraction. And that would look like this. Log base b, with our argument being x over y. We can expand this and simplify the argument being x over y, as log base b x minus log base b y. And then for the power, if we think back to exponents again, let's scoot some of this over. That way everything can fit. If we think about the power property for logs, if we have base b, x, and then this entire term is raised to the y, we get b raised to the xy, so we multiply them. For logs, we have log base b. Within the argument, it would be x raised to the y. Now, because this is an exponent for the argument and not the entire log, we can rewrite this as y times log base b of x. And again, that makes it easier to evaluate the argument within the log. So what does this look like with actual values? This all should be reviewed from last year, but obviously what you took last year might not be fresh in your mind, so this is a quick overview of that. It says condense, which means we want to condense it down to one log with no coefficients, because those coefficients should become exponents using the power property for logs. So I have that 1/2, so we'll have log base 5 of x. It's going to be x raised to the 1/2. I'm going to rewrite that as a square root, minus log base 5 of y raised to the power of 4. From here, the last thing that we can do to condense is we will divide because we're subtracting. So log base 5 square root of x over y to the power of 4. And then again, make sure you're linking your work using equal signs. The next one, we have 3 terms, so we should have 3 terms within our argument for the condensed log. We have log base 7 of x raised to the power of 8 plus log base 7 of 10 raised to the power of 2 minus log base 7 of y, and I'm going to rewrite this as the cubed root of y. From here, we can condense everything to one log base 7. This term is positive, therefore the x to the power of 8 goes in the numerator of our condensed log. Positive, so the 10 squared goes in the numerator. This term is negative, therefore the cubed root of y goes in the denominator. So we'll have 100 x to the power of 8 divided by the cubed root of y. If you left it as y to the power of 1/3, that's acceptable as well. It's just this it squeezes everything a little bit easier, so we don't have a ratio as an exponent. All right, example 3. Just a quick reminder, natural log is log base e, so we're going to see this quite often. So 6 natural log of x minus natural log of y plus 3 natural log of x plus y, and the x plus y is within the argument of that last log. So we'll have natural log of x raised to the 6, no power for this one, plus the natural log of x plus 3, that's going to be cubed. So now condensing this into our natural log, x to the 6th is positive, so that's going to go in the numerator. Now the term for the y is negative, so that's going to go in the denominator. And then the term with the x plus y cubed is positive, so that's going to go in the numerator. And do not expand, like the instructions only say to condense. It does not say simplify or, well, actually, no, this is simplified. If you were to expand this, that is not simplifying, okay? So don't do anything else with that inner term there. Technically, you could if you wanted to, but it's not necessary and it's a waste of time. It's inefficient. We'll save that for the next unit. All right, now we're going to reverse. We're going to expand. So I have 2 terms in the numerator, 1 term in the denominator, and then I also see a power that will have to be moved to the front as a coefficient. So we'll have log base 3. I'm going to separate the terms first. X plus log base 3 of y. Z is in the denominator, so we'll do minus log base 3 of z raised to the 5th. And then we'll have log base 3 of x plus log base 3 of y minus 5 times log base 3 of z. You can do this in one step if you want to. I just like to apply each rule within its own step. All right, now example 5, we have log base 4 of x to the 7th times 4 raised to the 3x plus 1. So we'll go ahead and separate the 2 terms. Log base 4 of x to the 7th plus log base 4 of 4 raised to the 3x plus 1. From here, we can use the power property. So we're going to have 7 times log base 4 of x plus, we have the 3x plus 1. Pull that to the front. Make sure that you use your parentheses for this, please. And then log base 4 of 4. Now, there is a property here. The base is the same as the argument, and when that happens, this is equal to 1. So what you could have done in the previous step is that we could already make this 1, and then that's going to pull the exponent down as the base. But technically, the process is that we use the power property, bring it around as a coefficient, and then log base 4 of 4 is equal to 1. So we have 3x plus 1 times 1, which means this is going to be just 7 log base 4 of x plus 3x plus 1. And then we're done. No other terms can be combined because they are not like terms. All right, example 6, we have log base 2 z. That will be positive because it's in the numerator. The next term is the y. We're going to subtract because it's in the denominator. And then sometimes this can be a little tricky. Even though we're multiplying the 2x plus 1 with the y, it's still in the denominator. So we're going to subtract. So we'll have minus log base 2 of 2x plus 1 raised to the 4th. Now we'll use the power property. This one stays the same. We're going to bring the 5 to the front as a coefficient. Same thing, we'll bring the 4. We'll have log base 2. And then in parentheses, we have 2x plus 1. And that completes this one. So these properties, they are not going away, especially if you plan on doing calculus. There's a topic called logarithmic differentiation. And again, these properties, it's used for the same reason. If we want to differentiate a complex function that involves logs, we are able to utilize logarithmic differentiation to make it easier to differentiate. So the natural base e, this stems from compound interest, compounding continuously, which is something you talked about in Algebra 2. And we will talk about it again in solving, which is the next unit, okay? So for now, we just want to utilize the properties of logs in this natural base e. So the first one is, just recall, ln. This is technically log base e of e raised to the 2x. We see that the base is equal to, well, the base of the log is equal to the base within the argument, and that's going to simplify as 1. So anytime you see this, it will just be equal to the exponent. The process for this is that we can use the power property, so that pulls the 2x to the front, and then we have natural log of e. And then we see the same process that happened in the previous example. This, I think people say it cancels out, but be careful with that. It becomes 1. So there is a bit of canceling out, but it doesn't just go away. It becomes 1. So we end up with 2x times 1, which is equal to just 2x. So you don't have to show this process. Just please understand where this is going. Okay, they are simplifying down to the exponent. Same thing here, but it's reversed. So now our base is 10, and then we have log. If you don't see a value, it's just log base 10, and our argument is 55. So again, this will reduce, and we are left with our exponent, which is 55. Again, the bases are the same, so they reduce to 1. Natural log of 1. So think about this. Again, it's log base e1. So the question is, what power can we raise e to get 1? That's going to be 0. And then same thing, what if we had log base 5 of 1? What do we raise 5 to the power of to get 1? 0. So this is why graphically, anytime that we are looking at that intersection, that intercept here, it's always going to be 1. Because the input for a log, if it's 1, the output will always be 0. So this is where logs equals exponents. So whatever log you have, we're basically looking for, okay, what can we raise this base to the power of to get the argument? That's going to be the exponent. So logs equal exponents. Lastly, we have log base 3 of 3. Same base as the argument, so we will get 1. Again, what do we raise 3 to the power of to get 3? 3 to the power of 1 is equal to 3. All right, the next video will be on characteristics. I hope this was helpful.